When we look into the abyss of a black hole, are we staring into a dead end of physics, or into a neuron of the cosmos itself? What if these cosmic monsters are not destroyers, but thinkers, processing the universe like a brain processes thought? Black holes are among the strangest and most extreme objects in the universe. They are formed when massive stars collapse under their own gravity, compressing matter into an infinitely dense point known as a singularity. This singularity is hidden behind a boundary called the event horizon, a surface so warped by gravity that not even light can escape once it crosses over. To understand why black holes fascinate physicists, we need to look at their relationship with space-time. According to Einstein's general theory of relativity, mass and energy bend the fabric of space-time. A black hole represents an extreme case of this bending, a well so deep that space and time themselves become radically distorted. Near the event horizon, time slows relative to an outside observer. To someone falling in, however, time would appear to pass normally until they reach the singularity where our known laws of physics break down. What makes black holes especially mysterious is their relationship with information. In classical physics, any object falling into a black hole should be gone forever, erased from the universe. But in quantum mechanics, information cannot simply be destroyed. This paradox lies at the heart of modern black hole research. Stephen Hawking's work in the 1970s introduced the concept of Hawking radiation, in which black holes slowly evaporate over vast timescales by emitting tiny amounts of radiation. If this is true, then black holes are not permanent prisons. But if they evaporate completely, what happens to the information they once contained? Is it lost forever, or encoded somehow in the radiation itself? This puzzle is known as the black hole information paradox, and it has pushed physicists to explore radical new ideas. One of the most compelling is the holographic principle, the suggestion that all the information inside a black hole might actually be stored on its surface, the event horizon, in 2 dimensions. In other words, a black hole might act less like a bottomless pit, and more like a cosmic hard drive, compressing data about everything that has fallen into it. In this light, black holes begin to look less like destructive voids, and more like potential processors of information, entities that transform, store, and perhaps even transmit data at the most fundamental level of reality. At the heart of the black hole mystery lies the question of information. Physics tells us that the information about the state of matter cannot simply vanish, even if the matter itself is destroyed. When applied to black holes, this principle forces us to ask, where does the information go? The holographic principle offers a radical answer. Proposed by Gerard Tufte and Leonard Susskind in the 1990s, it suggests that the 3-dimensional contents of a black hole are effectively encoded on its 2-dimensional surface, the event horizon. In this model, every particle that crosses the horizon leaves an imprint on this cosmic boundary, like grooves on a record. The volume of a black hole, then, is not the true keeper of data, its surface is. This reframes our understanding of black holes from devourers of reality to storage devices of staggering efficiency. This idea becomes even more intriguing when we compare it to neural networks. In the human brain, neurons don't store all information within themselves. Instead, it's the connections, the firing patterns, the synapses that encode memory and thought. Similarly, black holes may not contain information in their depths, but rather process and encode it on their boundaries. Just as neurons fire in rhythmic, complex patterns, black holes may radiate information back into the cosmos in subtle encoded forms, through Hawking radiation. Some researchers go further, suggesting that the entire universe might operate according to a kind of holographic encoding, that the reality we experience is fundamentally an information structure projected from a deeper layer of physics. If so, then black holes are not exceptions, but exemplars, natural laboratories where the information architecture of the universe is laid bare. When we zoom out to the largest scales, the universe begins to resemble something uncannily familiar, a brain. Cosmological surveys mapping billions of galaxies show that matter is not spread evenly, but woven into a vast cosmic web. Filaments of dark matter and gas connecting clusters of galaxies, separated by enormous voids. Strikingly, this structure mirrors the appearance of neural networks, with galaxies acting like nodes and filaments like synaptic connections. At the centers of most galaxies lie supermassive black holes, anchoring their surroundings with colossal gravity. If we think of the cosmic web as a neural network, then these black holes might function as processing hubs, regions where information is gathered, compressed, and potentially redistributed. Just as neurons integrate signals from thousands of synapses before firing, black holes may serve as integration points of cosmic information, influencing galaxy formation, star cycles, and perhaps even the flow of information through space-time itself. Computer simulations have revealed that the distribution of galaxies in the cosmic web and the connections of neurons in the brain both follow scale-free networks, systems where a few nodes dominate connections, while most remain lightly linked. This statistical similarity suggests that the universe is not just visually, but structurally analogous to the brain. Both are efficient architectures for transmitting and processing information. If black holes represent the neurons of this cosmic brain, then the universe may be more than a passive expanse. It could be an active computational system, evolving patterns, connections, and perhaps even forms of cognition on a scale far beyond human comprehension. If black holes act as processors within a cosmic brain, the next question is inevitable: what is the universe computing? One possibility is that the universe is engaged in a vast act of self-organization. Just as neural activities give rise to patterns of thought, cosmic processes might be generating emergent structures of complexity, galaxies, stars, and life, as outputs of an information-driven system. In this sense, black holes could be performing the role of integration and transformation, ensuring that information never stagnates, but continually reshapes the cosmic order. Another implication concerns consciousness itself. If the large-scale structure of the universe functions like a brain, then perhaps consciousness is not confined to biological organisms. Instead, it may be an emergent property of the cosmos, a phenomenon that arises whenever sufficient complexity and information flow exist. Black holes as ultimate information processors may be nodes in a universal consciousness, operating on scales that dwarf human awareness. There is also the tantalizing prospect that the universe could be engaged in computation with a purpose. Some theorists speculate that reality may resemble a simulation, where physical laws are the code and black holes are the ultimate processing units. In this framework, the universe could be calculating its own future states, optimizing for stability, or even exploring configurations that allow observers like us to exist. These implications blur the boundaries between physics, philosophy, and metaphysics. Are we individual sparks within a cosmic neural network? Are our own conscious experience microcosmic reflections of a universal mind? If so, then black holes are not the end of knowledge. They are the very synapses through which the universe dreams. Perhaps the most haunting question is not whether the universe thinks, but whether we ourselves are its thoughts. Each human mind, each fleeting moment of awareness, could be compared to a single flicker in a cosmic storm of cognition. We live and die in the span of a breath, yet the universe, with its vast neural web of galaxies and its black hole synapses, may continue dreaming endlessly. Standing beneath the night sky, we may feel small, but if this vision is true, then we are not separate from the universe's mind. We are integral to it, the sparks of self-awareness through which the cosmos reflects on its own nature. In black holes, we see not only the mysteries of physics, but perhaps also the mirrors of thought on a grand scale. So next time we look into the abyss, let us remember, it may not be empty. It may be alive with computation, memory, and dreams. The darkness of a black hole could be the pupil of the universe itself, gazing back at us as we try to gaze into it. If this journey through cosmic minds and black hole synapses resonated with you, help the signal spread. Like this video. Share it with someone who wonders about the mysteries of the universe, and subscribe to the Omega Signal to keep exploring the unknown beyond. Your engagement helps fuel future explorations into the deepest questions of existence. This is the Omega Signal, signing off.